Hey guys, in this final lecture video on Lewis structures, we are going to now talk about some exceptions to the octet rule. So previously, you guys, we've presented lectures on how to build basic Lewis structures. You've done some practice with that. We talked about the concepts of resonance and formal charge and how we can use these concepts to identify which is the best candidate Lewis dot structure and build resonance hybrids to more accurately represent what molecules actually look like. In this video, we are going to move even beyond that, and we're going to look at different types of compounds that form that basically break the rules, some of the rules that we talked about before. And it turns out that these compounds that break the rules have some very important applications. So, for example, one of the things we're going to see is that in the formation of so-called free radicals, which you guys might have learned about in a health or nutrition or biology class, are actually examples of these Lewis structures that violate this octet rule. So let's go ahead and jump in here. We'll start off with our first set of compounds that violate the octet. And this set of compounds we're going to call odd electron species. So odd electron species. So free radicals is the really rigorous name, the definition that we're going to put out here that define this whole category. Molecules and ions with an odd number of electrons in their Lewis structures are called free radicals. And it turns out that these guys have two very important properties. First off, they're very unstable. And by virtue of this instability, it turns out that they're often highly reactive. Okay? So if we look at an example here of what I'm talking about, let's say I ask you to draw the Lewis dot structure for NO. Well, nitrogen contributes 5 electrons, oxygen contributes 6. We are going to end up with 11 valence electrons, which of course is an odd number. And so when we start building up the Lewis model, no matter what we do, and I want you can pause the video and play around with this. I can put the electrons wherever I want here. There's no way that we are going to satisfy octets for both atoms. It simply won't work. Okay, so but nevertheless, we find that this molecule NO does in fact exist. In fact, NO is something that is oftentimes produced as a byproduct of combustion processes and the like. And this molecule that's formed, because it has this incomplete octet, this nitrogen atom does not have a full outer shell, a full valence. It's going to be, as I said, very reactive. Which means that, for example, if you were to put this NO molecule close to other molecules, it would be much more likely to react with that other compounds and form new chemical species. Okay, which is the reason for the negative health effects. So free radicals, and for example, NO in particular, if you breathe in a lot of this stuff, it will actually cause rapid burning, spasms, and swelling of the tissues in the throat because these NO molecules are sort of willy-nilly reacting with all the biomolecules lining your alveoli and lungs and the like. All right, so we know that, and you might have seen this again in a nutrition class, that there are molecules, protective molecules, in our bodies that serve the purpose of basically selectively and preferentially reacting with these free radicals before those free radicals have a chance to damage your body. So vitamin C, vitamin E, these are both examples of antioxidant molecules that will quickly go and react with those NO molecules or other free radicals that our bodies are exposed to, and thereby prevent this cellular damage. Okay, so some pretty fascinating chemistry there. Pretty complex biochemistry, of course, involved in this process. But when it comes to identifying free radicals, it's really a pretty simple method. All we have to do is first count the total number of electrons. Then look at that number, and if that number is odd, then of course you will see that you do in fact have a free radical. Okay, so for example, I could give you a list of molecules here. You need to be able to look at this list of molecules, A, B, C, D, and determine which, if any of them, are in fact a free radical? Well, I'm going to go through and simply total up the electrons here. And I encourage you guys to do this first, pause the video, and then come back and check. So carbon, oxygen, add them together, we're going to have a total of 10 valence electrons. Not going to be a free radical. CO2, we've got a total of 16 valence electrons, even, also not a free radical. N2O, that's again going to give us a total of 16 valence electrons, not a free radical. However, if you look at NO2, we have a total of 17 valence electrons. And this is in fact our free radical. Now remember, we saw this guy in one of our introductory slides on our Lewis dot models, right? And we saw how NO2 minus, we actually built up NO2 minus and saw a nice stable Lewis dot structure that we were all happy with, right? Well, NO2 minus is a nice and stable ion, right? Because it's basically satisfying the electron deficiency that's present in this NO2 that would make NO2, neutral NO2, a free radical. Okay, so odd electron species or free radicals are going to be our first example of exceptions to the octet rule. Now there's two more examples that we're going to look at in this mini lecture, right? And the next ones basically have to do with how many electrons are around a given atom, but are still going to have an even number of total electrons. So the first thing we're going to look at here is this idea of an incomplete octet. So the definition of an incomplete octet are basically any sort of situation where you end up with a stable Lewis structure that has less than 8 valence electrons around one of the atoms. So it turns out that this can happen, and it does happen relatively frequently. The good news, though, is that most of these exceptions are centered around boron and beryllium. Right? There are more than that, but the vast majority of the examples you'll see in this class are centered around boron or beryllium. And so if you were to draw out the Lewis structures for, say, BH3 or beryllium H2 or boron trifluoride, right? Or here we'd have some valence electrons around the outside. All of these situations are going to lead to a spot where that central atom, boron or beryllium, has less than 8 electrons. Boron will oftentimes have only 6. Beryllium will end up with only 4. Now, of course, I should mention here, hydrogen is sort of always the exception to the octet rule. But remember, when we're looking at this, what we're really thinking about is this idea that we're not filling up the outermost shell. So hydrogen fills up its outer shell with only 2 electrons, gets that noble gas configuration, and is good to go. But this does beg the question, right? For example, if we look at the structure that we just had for boron trifluoride, right? We saw that central boron atom had a total of only 6 electrons associated with it. But you might have looked at that Lewis dot structure and wondered, well, hey, wait a minute. Couldn't I have taken one of those pairs of lone electrons here and folded it in to make a structure that looks like this down here on the bottom? Okay, well, of course you could do that. But then the question comes down to whether or not you should do that. And in order to answer that question, we're going to go back to our good friend formal charge. And we're going to use formal charge to build an argument for or against the formation of a boron-fluorine double bond. So we'll notice here in the Lewis dot structure at the bottom slide here, this Lewis dot structure right here, when we form that double bond, we end up getting non-zero formal charges. If you calculate the formal charge, and we can put those here, I'll put them in blue, the formal charge on each one of these atoms in the structure up top here is 0. When I put in the double bond, we now have a +1 and a -1 formal charge. More importantly even, we're putting a +1 formal charge on the most electronegative element on the periodic table, fluorine, right? Not a very viable situation. So as a result, this structure illustrated up here, in green, is going to be the primary structure that we observe experimentally. And of course, the same sort of logic holds for the other boron halides. We're going to have, in each case, that boron atom surrounded by the halides, and we're going to keep all those electron lone pairs out there on the terminal halide atoms rather than folding them in and forming double bonds and placing non-zero formal charges. Okay, so these are our examples of incomplete octets. Now, our third and final example is this idea of expanded octets. And as you might guess, what we're going to be looking at is situations where you have more than 8 electrons around that central atom. So it turns out that if you look at atoms in the third row or below, and you go back to our electron energy diagrams from previous lectures, we'll see that once you go to that third row or below, you end up with d orbitals. D orbitals that can accommodate 10 electrons, remember, that are relatively close in energy to the energy of the other valence electrons. The result of having these d orbitals around is that you can actually accommodate more than 8 electrons around those atoms. Okay? And anytime you have an atom with more than 8 electrons in their Lewis structures, we call that an expanded octet. And I want you to remember, this can only happen if you're in the third row or below, because you need those close in energy d orbitals in order for this to be energetically viable. So some examples here are the arsenic pentafluoride, where we have a central arsenic atom with a total of 10 valence electrons around it. Sulfur hexafluoride, where we actually have 12 valence electrons around it. 10 and 12 valence electrons are very common for these expanded octet situations, and you can actually sometimes see examples where you have up to 14 valence electrons. We won't actually be looking at those examples in this class, but it's an interesting note to sort of file away. Okay, so just as we saw in the previous examples of incomplete octets, we now need to examine the question of, well, how do we know when to expand the octet? So it's probably no surprise that once again we're going to use the concept of formal charges. All right, so let's build this up with an example. Let's look at sulfuric acid, H2SO4. Up until now, right, you would have hopefully put together a Lewis model for H2SO4, sulfuric acid, that looks something like this, right? Where you have OHs coming off that central sulfur, everybody's got an octet, and then if you go back through and you assign formal charges, we see that sulfur has a +2, -1 for 2 of the oxygens, okay? Now, all things considered, this might look, reasonably well, reasonably viable candidate. Now, when you are basically in a situation like this, you always want to ask yourself and say, now wait a minute, is that central atom third row or below? If it is, then you want to ask yourself the question of, can I expand the octet in order to reduce the formal charge? Okay? And so we see that it is in fact possible to actually eliminate the formal charge in all atoms by expanding the octet and building up a structure that has 2, 4, 6, 8, 10, 12 valence electrons around that central sulfur atom. Okay, so only when you have third row or below, you can do this little check and see, well, can I zero out those formal charges? So in this case, the answer is yes, you can. You can zero it out. And as a result, this structure down here is going to be the preferred model, or the model that more closely represents the experimental reality. And of course, this can be verified. Right? If you look at experimental techniques, and we won't go into the details of the experimental techniques, but suffice it to say they show that the SO bond lengths on these two SO bonds without the hydrogen, so this guy and this guy, right, are in fact shorter than SO single bonds, and that is indicative of some double bond character, okay, which means that this sort of model is getting us closer to what's actually happening when we're looking at comparing our model to experiment. Okay, so our rule then is simply to expand octets in the third row or lower elements when we can lower the formal charge in doing so. Okay, so let's close with a final example here, XEF2. Let's build up the Lewis dot model, and we'll see that this molecule is an example of an expanded octet situation. So XEF2, the total number of valence electrons in this case, is going to be 7 for each one of the fluorines, 8 for the xenon, and adding it all up, we're going to have 14 plus 8 gives us a total of 22 valence electrons. We're going to put the more electropositive xenon in the middle, fluorines on the outside. We're going to come in, we are going to add in our bonding electrons. That uses up 4 of these guys and leaves us with a total of 18 electrons left over. So we'll carry that 18 electrons left over, then we're going to add in our lone pairs, fill up those octets, adding those lone pair electrons to the terminal atoms first, right? We can see that that used up a total of 12 electrons so far, and of course we still have 6 more. So then with those remaining 6 electrons, well, we're now in a situation where we need to add those to that central atom. But you'll notice we already have 4 electrons there. So previously you might have said, well, hey, we can't build this molecule, it's not going to work because there's already 4, I can't add the remaining 6. However, if we look at the periodic table, we'll see that xenon is in fact third row and below, right? It's down there towards the bottom of the periodic table, which means that these 6 final electrons can in fact be added, and we're going to add them around that central xenon atom, right? And then that will end us up with 0. We've used up all of our valence electrons, and we've come up with a structure that is illustrating this concept of an expanded octet, because we have a total of 10 valence electrons around that xenon. Okay, so in summary, we've seen 3 different exceptions to the octet rule. The first one is this idea of an odd number of valence electrons, free radical compounds. You simply add up the total number of valence. If it's odd, you got a free radical, and we know these guys are dangerous. We saw some interesting health implications there. We saw incomplete octets, right, where you have less than 8 electrons. And we saw typical examples of these involve boron and beryllium. And then finally we saw expanded octets. And we saw that in order to expand the octet, you must be third row or below. And in both cases, you either form an incomplete or expanded octet in order to lower that formal charge.